Now, the screen does not say complex numbers. The screen says understanding mathematical objects. And I'm just going to tell you this because this is the structure of what I'm going to say. And being the Maths Learning Centre, it's not technically my job to teach you complex numbers. It's technically my job to teach you how to learn anything. So I will teach you complex numbers anyway, but through that I would like you to learn how to learn anything in the future. So you're understanding a new mathematical object in the area of complex numbers, and these are the questions you should ask yourself in order to understand it. So you need to know what are they? So you have this new object called a complex number, and you need to know what complex numbers are, which means there's a definition, and there's also several examples to show you what is a complex number and what is not. You need to be able to tell when two of these new objects are equal to each other and when they're not equal. And you need to know different representations of them and how to convert between them. And that's the biggest part of the complex numbers assignment at the moment. And you should know connections between this and everything else. Okay, and this goes for everything. So matrices, for example, you need to know what a matrix is. You need to be able to tell when matrices are equal. You need to look at the different representations of them. Vectors as well work the same way. And it works even in the topic of vectors. You can say a straight line in three-dimensional space. There are multiple ways of representing it. How do I convert between those and that sort of thing? So that's what I'm talking about there. We want to know what we can do to our objects. So for complex numbers, I want to know how to do operations on them. So the things that we do with ordinary numbers, I want to know how to do them on complex numbers. I want to know what information I can find out about a complex number. I want to know how to do various functions on them. So with numbers, I can do squared and polynomials and square root and that sort of thing. I want to know if I can do those with complex numbers as well. And of course, I always need to know about connections between stuff. And then finally, you want to know what you can do with them. And most mathematicians don't care all that much about this question. So you want to know where you see them, like hopefully in real life or actually trying to solve problems using them. And you want to know what other stuff you can make with them. Complex numbers, not so good for that, but they are useful for solving problems. But I'm not going to tell you any of those because personally I don't use complex numbers in my own research because I do geometry, finite geometry, which doesn't use complex numbers. Doesn't even use real numbers, so that's irrelevant to me. But where you see them, what you use them for, I will tell you a few of those things. And sometimes with vectors, you want to know what new things you can make with them, and they make new objects. Okay, so that's what I'm going to run with, and I'm going to kind of flip between these different areas, but that's really what I'm going to be doing today about complex numbers. But in particular, the different representations of them and the different things that you can do to them is what I'm focusing on today. So, now obviously I decided to do this about 2 hours ago, so I have no fancy handouts and stuff to go with this, so you're going to have to just bear with me, but I will scan the things that I write and put them in my uni when I've finished. Okay. It may be until Monday. It may be Monday by the time it happens, but I will do it. Okay, so I will try my best to write neatly. So, let's... okay, so I'm just going to leave that one there. That's the one I'm recording. And so, for the benefit of those listening, I'm just keeping my list of understanding mathematical objects on on the other screen, but you won't be able to see that because the computer only records one of the screens at a time. So, let's just talk about what are complex numbers. And in order to answer that, I probably need to already jump into the different ways of representing them to begin with. There are 3 ways to represent complex numbers. And in order to have enough space to talk about what I want, I've just thought that I should probably put my paper this way. Okay, so there are 3 different ways to represent a complex number. The first way is the one that's in the definition of what a complex number is. And it's they call it the Cartesian form. Okay? Oh, crap. They call it the Cartesian form. Okay? You might also have heard it as rectangular. if you've been listening to me, as opposed to your lecturer, but some people call it rectangular as well. Okay? And that's the definition, is a Cartesian form. And so you define that a complex number is a plus bi for a and b real numbers, where I is a number such that I squared is 1. Okay, but that's what a complex number is in Cartesian form. Okay, and that's the definition of a complex number. All right, so all things in mathematics have definitions. You have to start somewhere, but that's the definition of what a complex number is. So while I'm at it, let's do some examples. You know, 3 plus 4i, right, is a perfectly good complex number. But so is just I is a complex number as well. And so is, 2 is a complex number because it's 2 plus 0i. Okay? 2 is a perfectly reasonable real number, and all the real numbers are complex numbers too. They're just special complex numbers. Okay? So, pi and the square root of 7 minus 38 on 15i. Okay, they're all complex numbers. And just note that you don't have to have whole numbers here or even fractions. They can be roots and ridiculous things because you're allowed to put any real number in that spot. It's just that most of the examples you're given have whole numbers there because it's easier to do the maths. Okay? Right, that's Cartesian form. Now, there is a second form, which is the graphical form, right? We can represent any complex number on a graph. That's a P, graphical, yeah. So the reason why it's called Cartesian form is because you can represent it on a Cartesian coordinate system. So the ordinary x, y coordinates that you know are actually called the Cartesian coordinate system, and so that's why it's called Cartesian form. So the number a plus bi, there's a and there's b, and that point is a plus bi. Okay, that's our graphical representation of a complex number. Okay? So every dot here represents a complex number. All the dots down here are real numbers. And so some people would label this as the real axis. And all the dots here are multiples of I. So if your dot is on this axis here, it's a real number. All the other dots are non-real. Okay, but everything on this picture is a complex number. So what we're actually doing is we're representing them as points in space. And we all know from our knowledge of how vectors work is that a point could just as easily be represented as an arrow from there to the origin if I wanted as well. So technically there's a third representation that I could represent it as an arrow that goes from there to there too if I wanted. Okay? But most of the time we represent them as dots. Okay? All right, and thirdly, there is the polar form. Okay. So your polar form has a different perspective of locating that point on the plane. So this point here can be located in a different way. You could say how far it is from the centre, and you could say how far round it is rotated from the real axis. And that's the polar form. So we can represent the polar form as well. I'm just going to put a gap there because this makes most sense here. So we can have r cis theta. Okay? So what that means in terms of the graph is this. That distance there is r, and that angle there is theta, and this point here is r cis theta. Okay? Theta is always measured anti-clockwise from the positive x-axis, or the positive real axis. So real numbers have theta being 0, so let's just do some examples of that. So a real number like 2 would be 2 cis 0, because it's 2 away from the origin and it hasn't been rotated at all, okay, because it's like here. Say I would be 1, because it's 1 long, cis pi on 2, because you would rotate 90 degrees and be here on the axis, and that would give you the point I, because it's 1 up on the y-axis, okay? So every complex number can be represented in that way, but I should point out that every complex number has multiple ways of writing it in polar form. Okay, they only have one way to write them in Cartesian form, but I could just as easily write I as cis, like 1 cis of 2 pi plus pi on 2, so 2.5, 5 pi on 2. And that's the same number, okay? Because what I'm saying here is that I might rotate 90 degrees to get to I, but I could just as easily rotate 90 and then another whole revolution and I'll be in the same spot. Right? Okay. So there are our 3 representations: Cartesian, graphical, and polar. So our Cartesian form is here and our polar form is here in terms of the picture. Now it is possible to convert between any one and any one of the others. Okay, so we already know how to convert from here to here, and we already know how to convert from here to here, because we know what the r and the theta represent in terms of angles. So I could have, 27 cis 17 pi, and I could go, well, it's 27 long and rotate it 17 pi radians, and I would get a point, and that would be that point, okay? But I want to know, how do I go from here to here? Like, how do I get from here to here? And how do I get from here to here? All right? That's really important to know how to convert between them, partly because you need to know, and partly because people keep asking you in exams. So you need to know that sort of thing. So we're going to convert between them. So that's going to be like a separate page because it won't fit neatly in my little categories here because I need to do arrows between them. So here we go. So Cartesian to polar. Cartesian to polar is much harder than from polar to Cartesian. So I'm going to do polar to Cartesian first. Okay, so polar to Cartesian form is extremely simple because you might have r cis theta. Well, that is the same as r of cos theta plus I of sine theta. And when you expand that out, you'll have r cos theta plus r sine theta times I. And look, this is already rectangular Cartesian form. It's number plus number times I. That's what it's supposed to look like. So as an example, for example, we might have 7 cis pi on 3. And that would be 7 cos pi on 3 plus I sine pi on 3. And let's see, cos pi on 3 would be, what's that? Would be a half. And sine pi on 3 would be root 3 on 2. And so I've got 7 over 2 plus 7 root 3 over 2 I. And now it is in Cartesian form. Extremely simple. No need to go to the graph. You just expand it out. And that cis stands for, see, the C stands for cos, the I stands for I, and the S stands for sine. Okay? Cos, I, sine. Cos, I, sine. That's what cis stands for. Whoops, sorry. There's my whole example. So that CIS stands for cos, I and sine, which is reminding you how to expand it out. So this is actually very straightforward, much more straightforward than pretty much everything else in complex numbers. Okay, so the other thing we might want to do is go from Cartesian to polar, and that's much harder. Okay? So to go from Cartesian to polar, I have to go via the graph, or graph if you prefer. The polar to Cartesian, you can skip the graph, you can just do it on paper as a calculation, but from Cartesian to polar you must use a graph to do it. So I'm going to do it as an example because it won't make any sense in formulas as far as I can tell. So, let me just do this one. So I've got the number 1 plus I. Ooh. The number 1 plus I can draw on my graph as here. Here's 1 and here's I. So 1 plus I is here. Okay, 1 on the x-axis. Did you just lose brightness up? No, you didn't. Okay. Yeah. Don't know why it did that. I don't want to break it, so I've probably already broken it. So this is 1 plus I here. It's 1 on this axis and 1 on this axis. So that's how to draw it. And to find it in polar form, I just need to draw it as the length and the rotation. So here's the length there. And I want to know what that angle is there. Okay? Because that will be the r, the length will be the r in polar form, and the angle will be the theta in polar form. So I can do that with ordinary everyday geometry because I've got a triangle there. Because my triangle just here says, just drawing a triangle, I have 1 here and 1 here. That's my theta there, and that's my r here. So, well, that's r there, and that's theta there. So r is root 1 squared plus 1 squared, which is root 2, and that's from Pythagoras' theorem. And theta, I would get from trigonometry. Tan theta is 1 over 1. So theta is whatever tan inverse of 1 is, which is pi on 4. Which I knew anyway by just looking at my picture because that's half a square. Okay, so therefore my number 1 plus I is in fact equal to root 2 cis pi on 4. Okay, the r is root 2, the angle is pi on 4. Now you need to be extremely careful when you're doing this because when you do that tan inverse, you won't always get the actual angle that you need to get to that spot. So as another example of Cartesian to polar, right. Minus 1 plus I can draw that too. And that's here at minus 1 and plus I, so that's here. That's that point just there. So minus 1 on the x and 1 on the I. And I need to know this length, that's the r, and this angle because that's the theta, because the theta always goes from here to there. Oh, sorry. Okay. So, I can do the same thing, but my triangle's now here, see? still blue. That triangle there is the triangle I'm going to use to do the conversion. So I've got this triangle here, and it's -1 going that way, and 1 going that way. And so I can figure out what this angle here is, right? But that's not theta, because theta is actually over here. So anyway, my length r is going to be the same. So r is going to be this length here, squared, plus this length here squared, which is still 1 plus 1, which is √2. But my theta, however, is going to be, well, it's still going to be arctan, right? I'm still going to go this divided by that, opposite over hypotenuse. So tan theta is the opposite over the adjacent, opposite over adjacent, which is -1. And if I get my calculator to tell me what tan inverse of -1 is, it's going to tell me minus pi on 2, minus pi on 4. But this angle here is not minus pi on 4. Minus pi on 4 is down here. Minus pi on 4 goes this way. So in fact, the angle I need to use is 180 degrees minus that angle there. So it's 3/4 of pi. Okay? So actually this is not correct. Theta is not equal to that. We actually can go, you know, tan inverse of -1 is negative pi on 4. So theta is in fact pi minus pi on 4. Okay, so, all right. I just wanted to point that out, and everyone is usually confused by that for quite some time. But the idea is that the angle is actually over here. It's not part of this triangle. When you do the tan to do this triangle, you're going to get the angle that's here. You need to figure out what the angle that goes from there is. All right. All right, so as I said, converting from Cartesian to polar is hard. Let's just go back to our original picture. And try and fix this colour. Can't do it. Oh, okay. No, I just... That's a bit better. Stop. Go away. Oh no.
Switch it up.
I don't know how. Okay, we're just going to have to deal with it. Sorry about that. Okay, so we've got our 3 forms. We know how to convert between them now. Going from here to here is really easy. Going from there to there is quite hard. And to get from Cartesian to polar, you have to go via this graph. Okay, you have to draw this, then do a calculation to figure out what these things are. Okay, so the next thing that we want to do on our list is to know what can we do to our complex numbers. So we want to get our complex numbers and we want to do stuff to them that we used to be able to do to ordinary numbers. So the things that we used to be able to do to ordinary numbers were plus, that is so bad. Sorry. We used to be able to do plus and minus and times and divide, and we used to be able to do powers as well. Okay? We want to be able to do all of those things with complex numbers, and then we're going to find out the things that you can do to complex numbers that we never used to be able to do to real numbers. Okay? So, we can do all of those things with complex numbers because it's just algebra in the end. And it's much easier to do plus and minus in Cartesian form. In fact, it's impossible to do plus and minus in polar form. And it's much easier to do times and divide in polar form. Okay? So that's one of the purposes of having different representations. It's to make it easier to do the calculations. And powers are heaps easier in polar form than they are in Cartesian form. But in the three forms, there is a representation of them. So in our Cartesian form, let's have a look at what these look like in Cartesian form. So in Cartesian form, adding is just algebra. 3 plus 4i minus plus 7 minus 3i. Well, it's just algebra, right? Because it's like 3 plus 7, which would be 10, and 4 minus 3 would be 1. So that's just adding, okay? And you're just treating it as it would with algebra. The I might as well be an x. Just pretend it's an x and work with it, okay? And subtraction works in exactly the same way. And so does multiplying by a whole number, okay? All right, so that's addition and subtraction. Plus and minus work really well with that, okay? And times is just algebra as well. So 3 plus 4i times 7 minus 3i. I just multiply them out, right? So 3 times 7 is 21. 3 times minus 3i is minus 9i. 4i times 7 is 28i. And 4i times minus 3i, well, the 4 times the minus 3 would be minus 12. And the I times the I would be I squared. Okay, so treat it as algebra. The difference between this and ordinary algebra is that I squared is minus 1. So every time I see an I squared, I can replace it by the number minus 1 and do more calculations. So let's see, we've got 21 minus 9i and plus 28i will come out to 19i. And I squared is minus 1. So let's see, 21 minus 12, so that's 21 plus 12, so 33. 33 plus 19i. All right, some people remember the direct formula for how to use these numbers to produce these numbers in one go, but I can never remember that, and more power to you if you can. That's great, go for it. But I can't remember that, but I can remember algebra, and I can remember that I squared is minus 1, so that is better for me. So, yeah. Right, and division is a world of pain. Okay, so we're going to have to... Yeah, here we go. Well, compared to addition, it's a world of pain, but then it was before, right? Even with ordinary numbers, division was never as easy as anything else. So 3 plus 4i divided by 7 minus 3i. I'm going to use the same ones just because I can't be bothered thinking of a new example. So look, that's a perfectly good number, right? It'll come out to some complex number. And as long as the bottom's not 0, you're always allowed to do division. You can even do 0 divided by anything, and the answer will always be 0. But the problem is that we really want to write it as something plus something I. Okay, because all complex numbers can be written in that way. So we would prefer to not have to have all those horrible i's on the bottom. So what we need to do is we need to do what we always do when we try and deal with fractions and multiply the top and bottom by something so my fraction's easier to work with. Because that's how we used to have to add fractions. When we were first learning fractions, we had to multiply the top and bottom by something to make it look prettier. So we're going to do the same thing now. And we need to multiply the bottom by something that's going to make it real, because dividing by real numbers is extremely easy. So before I'm going to write this example again in just a moment, but just down here, no, you'll get to it. Dividing by real numbers is really easy, because when you divide, you can just divide things separately, because you know that 2 plus 6 then divided by 2 is the same as 2 divided by 2 plus 6 divided by 2. So I can expand brackets with division, and so once I've got that, I can just expand the brackets. So I need to times the bottom by something that's going to make the bottom real. and I have to times the top by the same thing, or the fraction isn't the same fraction. Okay, and here's where a little bit of knowledge that I haven't told you yet is going to come in handy. We'd like to multiply this by something that makes it real, and the thing that you should multiply it by is 7 plus 3i. So switch this thing in the middle to a plus. The reason that works is this is a difference of two squares. So when you expand the brackets, you'll get 7 squared plus 21i minus 21i minus 9i squared. Okay, so the i's in the middle cancel each other out, and I squared is real already because it's minus 1, and so everything, all the i's disappear when you do that. So I have to multiply the top by 7 plus 3i as well and expand that out. So 21 plus 9i plus 28i plus 12i squared on the top, and 7 squared is 49 minus 9i squared on the bottom. Sorry? Yes, which is plus 9. Thank you. So the point that Adele has so eloquently made is that I squared is minus 1, so minus 9 times I squared is minus 9 times minus 1, which is plus 9. So the bottom is now 49 plus 9, which is 58. Okay, and the top is, well, see that I squared is minus 1 as well, so I've got 21 minus 12, which is 9. So 9 plus 37i on 28. And to be completely rigorous, I can divide each of these by 58 separately, because that's how division works. You can expand it out over plus. So if I really, really wanted to write it in Cartesian form, where I have to have something plus something I, that's what I would do. So that's not that hard, right? But, you know, it takes a while. Great. That just leaves powers, right? Now, it would be awesome if we could do complex number to the power of complex number, but we're just not going to go there. And it's not possible at the moment using Cartesian form. That's not actually possible using Cartesian form. You have to use polar form to do that, and I don't think you're even taught it in your lectures, so I'm not going to tell you. But powers, it's the same deal. You just use algebra. You know, 5 plus 7i cubed, you just expand it out, right? In the way that you would normally expand everything that had a cube. It would be take a while, because you'd have 5 plus 7i, 5 plus 7i, 5 plus 7i. And you expand all those brackets out, and all the I squareds would become minus 1. And in fact, you're going to get an I cubed as well. And I'm going to tell you a very useful fact about powers now that's going to be extremely helpful. So watch this. You see, I is I to the power of 1. Okay? And then I squared is negative 1. Right, we're good with that. To get I cubed, we're going to have to times by I again, because that's I times I times I, which will be negative I. And then to get I to the power of 4, I'm going to have to multiply by I again, and so I'm going to get, let's see, minus I times I would be minus I squared, and I squared is minus 1, so I've got minus minus 1, which is plus 1. And then I to the 5, when I multiply it again, will be I again, because it will be 1 times I. So the powers of I go in a circle. So my powers are, you know, this would be 1, 5, 9, and so on. These are the powers of I that go here. The powers of I over here are like 2, 6, 10, and so on. The powers of I that all come out to minus I would be 3, 7, 11. The powers of I that come out to 1 would be 4, 8, 12, and so on. Okay? So with minus 1 on its own, every other power is the same, but with I it's every fourth power, because well, it actually rotates around. I should say that this works with division as well. So if you actually start with 1 and divide by I, you'll be going this way, and so you'll get minus I. So dividing by I goes the other way. So this is also I to the minus 1, and this is I to the minus 2, and I to the minus 3, and so on. So that's really useful when you're expanding brackets, because up here in this other problem, we're going to get an I cubed, and we'll be able to automatically replace that by minus I when we get to it, and that'll make the whole algebra heaps easier. So that's Cartesian, and that's how to do our powers in Cartesian form. All right. Polar form is sort of nice. I need to find the edge of my paper. So for polar form, plus and minus, don't even try. Convert to Cartesian form and then add them. Okay, so polar form will not allow you to add and subtract at all. Okay, so you can't add or subtract them if they're in polar form. You have to convert them to rectangular form first. Times and divide, awesome, not awful. So if you had like 3 cis pi times 4 cis pi on 3, well, you times the lengths and add the angles. So 1 1/3 pi would be 4 pi on 3. So what did we do? We multiply the r's and we add the thetas. Okay? Okay, so that is really so much simpler than the expanding of the brackets. You have no clue what this number is just by looking at it, but you can draw it on the diagram and know where it is. And you can always expand out this cis, right, to figure out what the 2 bits of the Cartesian form are. Division is just as simple. I'm going to give me one that's actually going to work. So 12 cis pi on 4, 3 cis pi on 2. I'm going to divide them. Well, instead of multiplying the r's, I'll divide them. Instead of adding the angles, I'll subtract them. So I'm going to get 12 divided by 3 is 4. And pi on 4 minus pi on 2 would be minus pi on 4. So I divide the r's and subtract the thetas. So subtract the one that's on the bottom, right? So that's the awesomeness of polar form. It makes division easy. Because division in rectangular form was really quite difficult, but polar form quite straightforward, roughly. You have to get it to polar form first, of course. And powers are also easy. So if I had like 3 cis pi on 4 to the 3, say, well, you always do what the power says to the real number part, so to this bit. So that'll be 3 to the 3 cis 3 times pi on 4. So powers can be brought inside the cis as multiplication. So that was 27 cis 3 pi on 4. So I power the r, but multiply the theta. Okay, so that Cartesian form manages to bring all the operations down one level. Times comes down to plus, divide comes down to minus, powers come down to times. Okay, if there was something above powers, it would come down to powers. And that's why plus and minus don't work, because they have nothing to go down to. Okay, times is really a whole lot of addition at once, but addition is the bottom. You can't go further down than that, so that's why it's not going to work. Okay? All right, and this rule here will actually work with complex numbers too, but then you have to know what cos of a complex number is, which we're not going to go there. Okay, so that's pretty much it. That was my total list. But there are a few things that we can do now, and we have one more thing that we need to be able to do before I can draw the pictures, which was what everyone wanted me to talk about today. So we need to know the other things that we can do to them, the functions that we can do that we couldn't do on real numbers. So we've got all the squaring and the whatever, we've got all the powers, we've got the multiplication, division. We need to be able to do two other things. Well, three other things. So we've got some functions that we can do. So, firstly, we have the modulus function. That function there. Now, that function for real numbers was called absolute value. For complex numbers, I like to call it length or modulus. I tend to still call it absolute value anyway. But that's what it is. And it's literally the length as an arrow. So when I was doing that square root thing, that's how to find the length. So if I get a complex number, so in Cartesian form, if I've got a plus bi, then the length of it is the square root of a squared plus b squared. Note that you do not include the I in this calculation here. You ignore the I because this length concept comes from the picture. It's actually coming from this triangle here. We've got a here and b here to get to the point a plus bi. Okay? And it's this actual length along here. In polar form, r cis theta, well, the length of that is r. That's what r is. It's the length. And you knew that from the picture, right? So here is r cis theta, which is r this way and theta that way. R is the length. Okay? Cool. That's the length. And if we're going to learn a function, we should know how it behaves with everything else. So useful facts about the length are that if I have two complex numbers like z and w, and I do the length separately, on the outside I can expand length over multiplication. I can expand it over division as well. And I can bring powers inside the length as well. So the length of z in or out, length of z squared is the length of z squared. But I can't bring it in over plus and minus. Okay, so I'm not allowed to bring length in over plus or minus. I can only bring it in over times and bring powers out. Okay? All right? Awesome. Now that we are talking about length, I can show how to do a graph involving length. Okay? So, but one more thing, there's two more things that we can do. So my other functions are the real part, which takes the real bit. So the real part of a plus bi is a. And the imaginary part, which the imaginary part of a plus bi is b. Note that the I is not there. Okay, so the imaginary part is the real number that's next to the I. And finally, there's the conjugate. So the conjugate of a plus bi is a minus bi. So you switch the plus or minus. If it was a minus bi already, then you turn it to a plus. And for sis's, you'll turn the theta into a negative theta. The r will stay the same. Okay, so conjugation doesn't change the length of a number. And it's very important to know this extremely, extremely important fact that real and imaginary can't be brought in over anything. Real of z plus w is not real of z plus real of w, but conjugation can be brought in over anything whatsoever, no matter what it is. So if you've got like z plus w and you conjugate it first, it's the same as z conjugate plus w conjugate. You can bring the conjugate inside. It works for subtraction. It works for multiplication. And it works for division, and it works for powers as well. So conjugation can be brought inside anything you like, pretty much. It can even be brought inside length. So the length of z conjugate is the same as the length of z conjugate. Okay, so conjugation can be brought inside anything you like. Okay, that's one of the few things that you can do. In fact, conjugation is the only function that can be brought in over both addition and multiplication and powers. Okay, cool. So we have, that's functions. Now we have drawing pictures, okay? Now, this is a really big concept in maths. I've got 7 minutes, unless someone, unless they don't want to come in. But I'll go as long, I'll push it as long as I can, right? I might go till 10 past at least if they want to come in. So there's a really huge concept in maths that goes, every algebraic description has a picture description, and vice versa. Okay, so you've seen it in the vector part of your course, and you've got like an equation like x plus 2y minus z equals 0, and you know that that's a plane. Okay, so the object that is a plane, and that's a drawing in 3D, has an equation to go with it. But it also has a description in terms of what the coordinates of the points on that plane are. Okay? And that's the same in complex numbers, and you'll be given things that generally are about equations, and you have to figure out what the drawing that goes with it is, or vice versa. So, two things is that it's useful to think of the picture that you see in terms of x and y, because you know how that works. You know what a straight line formula is in terms of x and y, and so you can rewrite that in terms of the x bit and the y bit, and I'll show you what I mean by that. So suppose I had like this. I know what this is, so you can keep quiet. So suppose I had that. That's a straight line, right? If this was x and y, I would have x here and y here, and that would be the line y equals minus x. Right? Cool. But the thing is, this is not x and y. This is complex numbers. This x is the real bit, and this y is the imaginary bit. Because we know that a plus bi, the a is the real bit, and the b is the imaginary bit. So we know that x is actually the real bit of my complex number. Traditionally we use z to represent the whole number at once. And y is actually the imaginary bit of my complex number. In the sense of, so that is, z is x plus yi. Because if I have any point here, it's the x coordinate plus I times the y coordinate. So I can just rewrite that equation in terms of x and y, in terms of real and imaginary. It was y equals minus x, right? So now its imaginary part of z is minus the real part of z. Ta-da, it's an equation about complex numbers now. Yep?
When you write the imaginary part of it, do you include the I?
No.
Or is it just B only?
It's just the b. So for those who are listening on the recording, I was just asked, when you find the imaginary part, do you include the I or is it just the b? And the answer is it's just the b. Okay, so the imaginary part is the b that goes next to the I, but not the I as well. Okay? So technically the imaginary part is actually is still a real number, because it's just whatever real number is next to the I. So you strip away the I to do that. Okay, and that's what that is. I mean, technically when it said what is the set of complex numbers that this is, I would say it's the set of z such that the imaginary part of z is equal to minus the real part of z. Because technically it's a set, right? So I have to write it with the curly brackets because that's a set. Okay. Right. So most things can be done that way, okay? And you can actually convert from some things that are written in terms of... anyway, I'll show you. In terms of absolute values or moduluses, you could convert them to be in terms of x and y. So suppose I had this. The length of z plus 1 is equal to the length of z plus 2i. So that you can tell, I put a cross on my z's, so if it doesn't have a cross on it, it's a 2. Because my 2's look remarkably like z's. Or sometimes just like question marks. So, right. That's saying, if we think it through, z is a random complex number. I want all the complex numbers such that when I add them to 1 and do the length, I get the same answer than when I add 2i and do the length. Okay? But I can just sub in z equals x plus yi, and it will tell me what the formula is as a line or whatever it is. Just say that, where x is the real bit and y is the imaginary bit. And that means I'm going to be able to draw it on an x and y axes. So x plus yi plus 1, x plus yi plus 2i. Okay? Now to find the length, if it's in Cartesian form, which it currently is, to find the length I have to write it as something plus something I. So this plus 1 is real, it's not attached to an I, so I can get this. And this 2i, I'm going to bring in with the other I. And now I can find the lengths. So technically x plus 1 squared plus y squared, x squared plus y plus 2 squared. Again, remember when you find the length, you don't bring the I down, you just square just the number next to the I. And I would expand it all out. Are you teaching here next? No, but I can if you want me to. See? Told you I'd push it for as long as possible. At this stage I would square both sides. Yep, to get rid of the square roots. And then I would expand all of this out, okay? Because the thing is that you don't have to remember these steps. The aim is to get a formula that's just in terms of x and y, and the first thing I think to do is to expand it out. So I've got x squared plus 2x plus 1 plus y squared is x squared plus y squared plus 4y plus 4. And look, all the x squareds and y squareds are going to neatly cancel each other out. And I'm going to get this awesome formula which says, let's see, 4y is equal to 2x minus 3. And so if I really want to, y is a half of x minus 3/4, which is a perfectly good straight line equation which I can draw on a graph. Yay! That's the quickest way. So lastly, all right, lastly, maybe two more. Okay, so every equation has a representation. You know, the real part of z is less than or equal to 5. Well, that's just saying that x is less than or equal to 5, right? Because the real part of z belongs on the x-axis. So here's 5. This is where x is equal to 5. And this is where x is less than 5. So the real part of z is less than or equal to 5 is that. I could draw very easily the real part of z is between, say, you know, minus 7 and 5. And I would just put that in. Because that's saying the real part being between minus 7 and 5, x is what the real part is. And so the x is between 7 and 5, so there's between 7 and 5. But I haven't said what y is, so I'm allowed to use every possible y, so I just go up and down. And finally, if I want to make a circle, This is the most awesome bit. Sorry. If I want to make a circle, that's the most easy thing to do with complex numbers because I just talk about lengths, you see. See, a circle of radius, say 2, with centre at, 2 plus I, right? That's all the points that are 2 away from 2 plus I. That's what a circle is, okay? All right? Which means it's all the points so that the distance between Z, let's call it Z, all the points Z, so the distance between Z and 2 plus I is 2, because they're 2 away, so the distance between them and 2 plus I is 2. And here is how to represent the distance between Z and 2 plus I. So all points, all points, so that this, the modulus of Z minus 2 plus I, is the distance between Z and 2 plus I. So if you see a circle, all you need is the centre as a complex number and the radius, and you can draw it. So one final example. All right, so suppose that's the point 3 plus I. And let's just suppose this is the point 3 plus 4i, just there. Well, that circle has centre 3 plus I, so I know it's Z minus 3 plus I, the length of Z minus 3 plus I, and the distance between here and here is 3, because it's from 1i to 4i, so I've gone 3 steps up. So that distance is 3. That's the formula for that circle in terms of complex numbers. One more. If I were to know what this formula is, right, Z plus I equals 3, I have to rewrite that with a minus because I need it to be Z minus something to know about the distance. So Z minus I is 3. So now because there's a minus there, it's the distance between this number Z and this number minus I. So here is minus I, and the radius is 3. And I think they're going to get really antsy now, so I'm going to stop. Where do I stop it?
Sorry, can I interrupt? Are you just about finished?